Hi
Good
there.
morning to Dr. Yabunka. Our group title is PN Junction. Our group member is myself Bhaskaran, Nalini, Nalina and Gunasundari. Okay. What is semiconductor? What is PN junction? Semiconductor is a material that can conduct electricity which is between metal and insulator. The example of insulator is glass and example for metal is copper. PN junction is one of the example of semiconductor material that can conduct an electric current in one direction and blocks the current in the opposite direction. This PN junction is a boundary between two types of semiconductor material called P-type with an acceptor density Na, and in the right region is N-type with a donor density Nd. The electrons density in the N-type region is almost equal to the donor density, and the hole density in the P-type region is almost equal to the acceptor density. PN junction is fabricated within a semiconductor crystal that is usually silicon. A P-dope and N-dope semiconductor is conductive, and the junction between them can become depleted of charge carriers. Non-conductive is depending on the relative voltages of the two semiconductor regions, and non-conductive layers can be manipulated to work as diode. PN junction is one of the semiconductor electronic device that works at the electronic action site, such as diodes, transistors, solar cells, LEDs and integrated circuits. The bipolar junction transistor is a transistor which consists of two PN junction in series in the form of NPN and or PNP. The PN junction is widely used in many applications such as rectification of AC signals, that is converting DC signals to AC signals. More than that, it is also used to detect radio signals, convert solar power to produce electric current, and used as switch in some electronic circuits. Now I pass to Nalini to talk about thermal equilibrium in PN junction.
My name is Nalini Krishna. Now I would like to continue our presentation with thermal equilibrium condition. In a PN junction without an external applied voltage, an equilibrium condition is reached in which a potential difference is formed across the junction. This potential difference is known as built-in potential VBI. After joining a P-type and N-type semiconductor, electrons near the PN interface tend to diffuse into the PN region. As electrons diffuse, they leave positively charged ions, that is known as donors, in the N region. Similarly, holes near the PN interface begin to diffuse into the N-type region, leaving fixed ions, which is known as acceptors, with negative charge. The region nearby the PN interface lose their neutrality and become charged, forming the space charge region or depletion region. Okay. By this figure, we can know that a PN junction is a thermal equilibrium with zero bias voltage applied. Electrons and hole concentration are reported respectively with blue and red lines. Gray region are known as charge neutral, whereas light red zone is positively charged and blue zone is known as negatively charged. The electric field is shown on the bottom. The electrostatic force on electrons and holes and the direction in which the diffusion tends to move electron and holes. The electric field created by the space charge region opposes the diffusion process for both electrons and holes. Electrons near the PN interface tend to diffuse into the P region. A carrier concentration profile at equilibrium is shown. The space charge region is a zone with a net charge provided by the fixed ion, that is donors and acceptor, and that have been left uncovered by majority carrier diffusion. When equilibrium is reached, the charge density is approximated by the displaced step function. Now I would like to pass this presentation to Nalina to continue about the forward and reverse bias. Thank you.
I'm Nalina. I'll be presenting about forward and reverse bias PN junction. In forward bias, the P-type is connected to anode and N-type to cathode. This allows current to flow. The positive charge applied to the P-type material repels the holes, while the negative charge repels the electrons. This results in holes and electrons moving towards the depletion region. This makes the depletion region thinner and less resistive. An applied voltage in the forward direction, as indicated, assists electron in overcoming the Coulomb barrier of the space charge in depletion region. At the depletion region, the built-in electric field and the applied electric field flows in different directions. When these two fields add, the resultant field at the depletion region is smaller than the magnitude of the original built-in electric field. If the applied voltage is high enough, the resistance of the depletion region becomes negligible and the current can flow virtually unimpeded. In reverse bias, the N-type material is connected to anode and P-type to cathode. The positive charge applied to N-type material attracts the electrons, while the negative charge attracts the holes in P-type material. This results in holes and electrons moving away from the depletion region, hence increases the thickness of the depletion region, making it more resistive. Under reverse bias, there is very little or no current. At the depletion region, the built-in electric field are in the same direction. When these two fields add, the resultant larger electric field is in the same direction as the built-in electric field. If the applied voltage becomes higher, the depletion region becomes thicker and more resistive. To forward bias the PN junction, the P side is made more positive so that it is downhill for electron motion across the junction. An electron can move across the junction and fill a vacancy or hole near the junction. It can then move from vacancy to vacancy leftward toward the positive terminal, which could be described as the hole moving right. The conduction direction for electron in the diagram is right to left, and the upward direction represents increasing electron energy. To reverse bias the PN junction, the P side is made more negative, making it uphill for electrons moving across the junction. The conduction direction for electrons in figure 2 is right to left, and the upward direction represents increasing electron energy. The applied voltage is proportional to the difference between the Fermi energy in the N-type and P-type quasi-neutral regions. The total potential across a semiconductor equals the built-in potential minus the applied voltage. I'll pass on to Gunasundari to continue.
I'm Gunasundari. I will be talking about rectifying and non-rectifying junction. In PN junction, there are two types. One is rectifying and one is non-rectifying. Non-rectifying junctions are called as ohmic contacts, which is an electronic component employing rectifying junction including PN diodes. Schottky diodes and bipolar junction are transistors. Ohmic contacts in a non-rectifying junction that a region in a semiconductor device that has been prepared so that the current voltage curve of the region is linear and symmetric. On the other hand, ohmic contacts are simply defined as one in which there is an unimpeded transfer of majority carriers from one material to another. For example, the contacts do not limit the current. The way to achieve such a contact is by doping the semiconductor heavily enough that tunneling is possible. It is usually to heavily dope the silicon region so that an ohmic contact is ensured, and suppose ND in the semiconductor is very large. The depletion region width at the metal semiconductor interface surface becomes small. This process occurs in both directions so that contact shows are very little resistant and become ohmic. Both ohmic contacts and Schottky barriers are dependent on the Schottky barrier height, which sets the threshold for the excess energy an electron required to pass from semiconductor to the metal. For the junction to admit electrons easily in both directions, the barrier height must be small in at least some parts of the junction surface. To form an excellent ohmic contact, the barrier height should be small everywhere, and furthermore the interface should not be reflects electrons. As a summary, p-n junction has two types. One is n-type and another one is p-type. p-n junction are formed by joining n-type and p-type semiconductor materials as shown below. Since n-type region has high electron concentration and p-type is high hole concentration, electrons diffuse from n-type to p-type. Similarly, holes flow from diffusion of p-type side to n-type side. However, in p-n junction, when electrons and holes move to the other side of the junction, they leave behind exposed charges on dopant atom sites, which are fixed in crystal lattice and unable to move. On n-type side, positive ion cores are exposed. On p-type side, negative ion cores are exposed. An electric field formed between positive ion cores in n-type material and negative ion cores on p-type material. This region is called diffraction region. Since the electric field quickly sweeps free carriers out, hence the region is depleted of free carriers. Most of p-n junction is used in diode application. The use of commercial available in p-n junction diodes such as isometries has been favorable reported for X-rays and very high energy charged particles. The purpose of this study was to evaluate the suitable of p-n junction diode as a radiation probe of automatic isodimeter. Thank you.